acidification, increasing ocean acidification, declining reef health. We have three participants today. Nina Keul is a PhD student in marine biogeosciences at the Alfred Wegener Institute in Bremerhaven, Germany. Adina Paytan is a research professor at the Institute of Marine Science at UC Santa Cruz in Santa Cruz. And Robert Riding is a research professor in the Department of Earth and Planetary Sciences at the University of Tennessee in Knoxville, Tennessee. And with that, we'll get it started with Nina.
Thank you. My name is Nina Keul, and I'm doing my PhD in Germany at the Alfred Wegener Institute, and I'm going to present you some of the results of my PhD. I am working on Foraminifera, which are an interesting species to work with because they are producing about 1/4 of the oceanic calcium carbonate production in the ocean. And what we see is that it's counterintuitive, so with a decreasing carbonate ion concentration, just as it's happening when ocean acidification is happening, carbonate ion concentration decreases. So in our lab experiments, we saw that the foraminifera growth rates actually increased. And I'm going to give you the background so you can understand why this is actually counterintuitive. The atmospheric carbon dioxide concentration since the Industrial Revolution have been increasing steadily from about 280 parts per million up to 390 parts per million, which is the level we have today. And future predictions go as far as over 800 parts per million carbon dioxide concentrations at the end of the century. About 1/3 of the carbon dioxide has been taken up by the ocean. And just to put a picture to it, so every single day the ocean is taking up the equivalent weight of about 6 million middle-sized cars, which is a lot, and if you would put it into a traffic jam, this would reach from here over to Germany and back. So this is the weight of carbon dioxide being taken up by the ocean on a daily basis. First, when this was discovered, people thought of it as a good thing because this would actually help to minimize atmospheric carbon dioxide concentrations. But however, when carbon dioxide is being taken up in the ocean, an acid is being formed, and this acid causes problems. And as you can see over there, I'm not going to go over the whole chemical background, but just to line out two important things. When this acid is being formed, the pH is dropping. So the pH is what we use to measure the level of acidity in the ocean. And the drop in pH from pre-industrial values to today values has been about 0.1 units. This might sound really small, but actually, since the pH scale we are using is a logarithmic one, this drop in 0.1 units is actually associated to an increase in acidity of 25%. And next to the pH drop, carbonate ion concentration is also going down. And this is very important because carbonate ion is the building block of calcium carbonate. And calcium carbonate is what all those marine calcifying organisms use to build up their structures. And the way calcification is proceeding is that those organisms, they pull out the carbonate ions, building up their structures. And in order to be able to do this, there needs to be a certain amount of carbonate present in the ocean. And if there's not enough of this carbonate ion present, calcification is hindered. And we think of it as a threshold value. So if there's enough carbonate ion concentration above this threshold value, we call the waters oversaturated, and calcification can proceed very easily. Whereas if there's less carbonate present than this threshold value, we call the waters undersaturated. And undersaturated waters might affect calcification negatively because the calcification process itself might slow down. This is what I actually was really interested in. So what I did, I used Foraminifera. Thank you. I used Foraminifera, those are the little guys over there, and I subjected them to different carbonate ion concentrations, just like what would happen in ocean acidification events. And actually what we saw is that when carbonate ion concentration went down, like the building blocks went down, the availability of the building blocks, the growth rates increased. So this actually tells us two things. That apparently the species I used is not depending on carbonate ion concentration for calcification, and thus they may not be affected that negatively by ocean acidification. However, we have to keep in mind that the nature is really complex, and I'm presenting you results from one species, from one experiment, and this has been done in isolation. So we pulled out the organism from the natural habitat, put it into a petri dish, and conducted our experiments. So actually what is happening out there in the wild, we don't know. We can't tell from this experiment. It's like if you have a big puzzle and you just look at one puzzle piece. It's very interesting to look at it, but in order to get the big picture, you have to do more experiments. You have to look at a wider range of species. You have to look at different other mechanisms. So I'm presenting you one piece of the puzzle, which is interesting, which is good to see the big picture. But actually, in order to look at the big picture, you need to look at bigger systems. You need to look at bigger ecosystems. And I'm actually really happy to hand over to Adina, because she was able to do that, and she's going to tell you about it.
Thanks, Nina. As Nina said, most of the information we have about the response of organisms to ocean acidification is based on either modeling or laboratory experiments where you take one organism, put it in a jar, manipulate the conditions under very controlled conditions so you know exactly what is in that jar, and then you measure the response rate. However, as Nina mentioned, in the natural environment, things are more complicated because we're not talking about single organisms, we're talking about ecosystems. Also, most of these experiments, because of limitations of our lifetime, were restricted to days, months, at most years. We know that ecosystems and organisms evolve and adapt and can adjust to conditions in nature. So I was lucky to find out or stumble almost into a system where natural conditions are such that there's low pH that has been there in submarine spring for long thousands of years. These systems are quite abundant all along the Caribbean coasts, and what these systems are, you can see here, are submarine springs where brackish water discharges, and these brackish water has low pH and low saturation conditions, and ecosystems have been evolving and growing there for many, many years. And we can go over there and look at the responses of this ecosystem along transects from close to these springs off further away to the springs within the same environment. When we did that, we found very interesting things. First of all, to our surprise, we found that some corals were able to grow at these low pH conditions. Now, these are not just low pH, they're extremely low pH. The conditions are undersaturated with respect to aragonite. But there were only 3 species that were able to do that, and there's many, many more species of corals in that environment. So if you go just 20 meters away from that location, you get a lot more corals, more diversity of the corals. If you see over here, the species richness decline, the size of each colony declines for these species, and the density or the number of corals per unit area declined when you get closer to these discharge sites. So it's kind of a mixed news. On one hand, it's kind of encouraging that certain corals can actually survive and calcify and have been able to adapt to these low pH conditions. However, these are very select and few corals, and specifically these corals are not the reef-building corals for the Caribbean reefs. They tend to grow slowly in patchy, dislocated colonies, and they don't build the reef framework as we know it. And the implications for that is that all the organisms and people that depend on this beautiful ecosystem with its structures may be negatively impacted by the fact that we'll see this change. But because these organisms actually calcified there that also provided an opportunity to try and study what is it, how can they actually grow in such conditions when we thought they wouldn't be able to. And for that, we took some cores of these corals. We drilled the corals and patched it up so it doesn't die after that, and then did CT scans like you do in the hospital on these corals in order to look at the extension rate, or how much the coral grows every year, how many centimeters it accretes every year. We looked at the density of the carbonate that this coral precipitated, and the blue colors here are low density, the yellow colors are high density, and we also looked at how much boring or holes, cavities, that organisms that after the coral dies can go in and eat it up or disintegrate it have over there. And as you can see here, the extension rate decreases only when you get to very low undersaturation. When it's in the intermediate, they still grow. So they're able to grow nicely. However, at that unit time of growth, they don't put as much skeleton down, so their density is lower. And calcification, which is the product of extension times density, therefore decreases, while the boring or the holes that build up the structure of the corals increase significantly. Probably because they're less dense, all sorts of worms and clams and other organisms have an easier time making holes in them. The implications for that is, again, there's going to, these reef structures are not going to be as solid and robust, and they might be impacted by hurricanes, or they may fall apart. So in all, we're seeing that the response to ocean acidification varies significantly between species. It varies between environments. And while single corals may have a chance to survive, it looks likely that the coral reefs as a habitat as we know it may suffer consequences, and it would be very different from the coral reefs we know today and that we depend on today.
Good. Thank you, Adina. Robert Riding from University of Tennessee. We've been looking at the longer-term dimension of what's happened to reefs over the last 15,000 years. And we've been able to do this because the International Ocean Drilling Project cored reefs in Tahiti in the South Pacific in 2005. And they got a record of about 15,000 years of reef growth. And we looked at these cores, and we found that in the reefs prior to 5,000 years ago, the cavities in the reefs were cemented up and filled organically by calcified bacterial mats, stromatolites. And they really were thick crusts. They filled up the available space below the reef surface. So the reef grows, but as the reef grows, it's an open framework. And as it gets darker, most organisms stop growing, but the bacteria can grow in there, and they fill up the reef, and they effectively cement it and lithify it and make it much stronger than it would otherwise be. And these crusts are up to about 20 centimeters thick. They can in very framey reefs, very cavernous reefs, they can be as much as 80% of the reef frameworks. They're really a very substantial calcium carbonate component to the structure. But after, from about 10,000 years ago to 5,000 years ago, the abundance of these crusts declined very rapidly, and they actually disappeared within a few thousand years. And that would substantially alter the strength of the frame. It would make the frame much more liable to storm breakage, because this is happening just a couple of meters below the surface. So it would make them prone to breakage, prone to fragmentation by hurricanes. The decline in the crusts, the microbial crusts, was at the same time as CO2 was increasing very rapidly. And CO2 increase, you can calculate it, should substantially change the saturation state. It should lower the saturation state. It should make it more difficult for organisms to calcify, especially bacteria, because bacteria, unlike the corals and the forams that Adina and Nina have been working with, calcification by bacteria is very simple. They don't seem to closely control calcification. It's really a response to the environment. So they're a much more sensitive proxy, probably, to seawater chemistry. So what we think we're seeing is ocean acidification, and we see that it's occurred very rapidly in the early Holocene, which is about 11,000 to 7,000 years ago. And that acidification was a natural acidification. It had nothing to do, unless cavemen were having much larger fires than we imagined. There was nothing human in this. This was simply the fluctuations of CO2 that have gone on all through glacial interglacial cycles for the last hundreds of thousands of years. So what we think is happening naturally is that during glacial periods, it's almost counterintuitive, during cold glacial periods, tropical reefs actually calcify more because saturation state is higher. And during interglacials, CO2 rises very substantially, and that lowers the saturation state. That causes ocean acidification. So if that's correct, what has happened in the last 15,000 years is that natural acidification has weakened reefs and made them much more prone to breakage. And you can see on the right-hand side there, you can see how the reef can really, it's so friable that it's not preserved as a framework. It's often preserved as really rubble. If that's correct, then what that means is that the reefs have become weaker naturally by natural ocean acidification. And so if the expected anthropogenic acidification that's expected to occur, that's going to impact the calcification of corals, for example, it'll be a double whammy for the reefs. The reefs are already weakened by natural acidification, and they're going to be weakened again then by the acidification effects that we see proceeding at the present day and are expected to increase over the next 100 years or more.
Thanks. We'll now open it up for questions.
Thanks. Lizzie Grossman, freelance, and this is a question to start for Nina. I'm wondering if you could clarify for us a bit more what you saw in your results, because I know it's a little bit early in the morning, but if I understood your results, they are a bit counterintuitive to what we've been hearing, and as journalists, when there is a study that turns up that does kind of run counter to the trend, it's really helpful to have a bit more of a contextual explanation so that our readers don't jump on us and say, see, this isn't happening. So if you could explain what you're thinking has happening as a result of these anomalies, or whatever else we need to know to put it in context, would be great. Thanks.
Yeah, so to put it in a context, I'm not the first one to look at the effects of ocean acidification on foraminifera. And the thing is, it's actually from an experimental kind of view, every person or every experimental researcher uses a slightly different approach. And others actually have seen that foraminifera growth rates decline as carbonate declines, which is like what you would expect to happen. And the way I can maybe try to explain it is that with respect to foraminifera, we were the first, or one of the first, to actually use like babies. So we used the first, the tiniest stage of a foraminifera you can have. So it could be that it's maybe a different in experimental approaches. I have to say my foraminifera, they don't have symbionts. So some foraminifera which have symbionts, they actually thought to do better under low pH because the photosynthesis process could be enhanced. But my foraminifera, they don't have symbionts. So this could not be the reason why they actually enhance the growth rates with decreasing carbonate. And as far as the mechanism part, it's, we can only speculate what actually happens. So we know from another experiment that the foraminifera, when they are producing calcium carbonate, that they hydrogen ions which are being produced in the same process, these hydrogen ions, they need to be expelled. And we actually see them occurring at the outside of the chamber of the calcified parts, so we know they're being pumped out. So maybe it's just easier for Foraminifera to do that if the pH outside is lower, because this would mean they would pump against a steeper gradient. But this is purely speculative. This is I just got the results in, so it's preliminary results. I have to speculate.
I think that both Nina's results and the fact that we see corals calcifying in other saturated conditions suggests that there is still a lot for us as scientists to understand about the calcification mechanism. This is not something we fully know, and there's lots of groups out there actually trying to study the genetics and physiology that is associated with the calcification process.
Hi, Ernie Balsarac with EOS. Just to follow up, Nina, you said your experiments were on a particular species. What led you to select that particular species for your work?
Did it let me use it?
Why did you select that one?
Okay. Well, I think every experimental researcher, they like to use the species which lives in their front yard. And I'm living in northern Germany, so we use the species which is actually abundant in the Wadden, which is the muddy shores of northern Germany. So it's a benthic coastal species.
Steve Benko with Physics Today. I have a question for Robert. You've looked at the long-term history of these reefs, and I admit I'm a bit surprised by what I heard. I didn't realize there was this long-term natural acidification that took place. My question is, how old are the reefs? I mean, you can go down beyond the 11,000 year period where this weakening began and see the actual cementing at the base of the reefs? And has it been a gradual weakening in the cores as the reefs build? I mean, I don't know. I'm new to this stuff. So if you could give me a little more context on the paleo history of reefs.
Yeah, sure, Steve. As you know, the glacial interglacial cycles, they build up, you have ice build up and then ice melting, so you have very large sea level changes. And that affects the reef preservation, because when the sea level goes down, you get erosion surfaces. So you'll have a lot of discontinuities in reef successions. So at Tahiti, in those particular cores, below about 15,000 years ago, I think there's a hiatus, and you don't have a continuous record. But what we see above 15,000 is that you start with quite a dense reef, so it's not really a framey reef. As the framework develops, that's what gives these cavities where the bacterial crusts can form. And so you get a framework that's rather cavernous and fragile, but it's strengthened by these, if you like, these late components of the reef, the bacterial components. That they cement really, they're like organic cements holding the reefs together. But then after 5,000 years, they've really gone almost entirely. And you have the framework, and it's very fragile. And we do see breakage. You do see a lot of storm breakage in reefs, but it's like all research, it opens up. You really need to go back and look at things with fresh eyes. So there are parts of the world where you got Barbados is one place, Papua New Guinea. You've got very nice raised reef successions, and it would be really interesting to go back to some of those localities and look at glacial reefs and interglacial reefs in terms of their framework preservation, the amount of storm breakage that they had. It'd also be quite nice going to do field work in Barbados in December.
Rick Lovett, freelance. Another question for Dr. Riding. Can you tell us, how much did the ocean acidity change, or carbon dioxide levels change naturally during that period of time compared to today?
Well, we're not the first people to calculate changes in seawater chemistry. Joni Klapers, who's sitting just over there, calculated some years ago that there was a 20% decrease in saturation state of the oceans from glacial to interglacial cycles. I think our calculations showed slightly higher values than that, but a lot depends on really some of the assumptions you're making when you're doing seawater modeling.
My question, can you relate that to atmospheric carbon dioxide levels?
Exactly. That's the starting point. We take the carbon dioxide levels from the Antarctic core data that goes back for, hundreds of thousands of years. And we use those CO2 values combined with present-day seawater values to calculate the saturation state that you get if you have more CO2.
But, can you give me a number so I can compare it to the pre-industrial level that we were always talking about? What was it when these bacteria grew?
Okay, I'll pass over to one of my colleagues, Liyuan Liang at Oak Ridge National Laboratory.
Okay, so my name is Liyuan Liang from Oak Ridge National Laboratory. So basically, we use 180 ppm CO2 10,000 years ago. And to the pre-industrial level was about 300. So it's almost doubling of the CO2 concentration. And so the pH change will be about 0.3 units. So that's a quite large change. 0.3 units of pH.
Other questions?
I'm Wynn Perry with Life Science, and I have a question for Adina. Could you tell us more about the 3 species that you found within 20 meters, and also what kind of pH we're talking about?
Yes. The 3 species that we found are these species over here, Porites astrioides, Porites divericata, and Siderastria radians. These 3 species in the Caribbean tend to form solitary small colonies, and they're not these branching big reef colonies. And the pH that we see gradients, I have it up here as saturation state and not pH, but the pH at the blue area, which is undersaturated, was about 7.6 pH units. And within meters, because these springs are focused discharge sites, within meters away from that, it becomes ambient pH, which is about 8.1 in this system. And these systems are very close to shore, right at the back reef. So if you go, a few tens of meters away from the springs, you see the complex reef structure over there with many, many more species. There's actually at the back of the room, there's a paper that was just published last week that has a lot more information about this study. So if you want to pick it up, there's.
Rich Monstersky with Nature. For Dr. Paytan, I wonder, you said that these are brackish springs, so is pH the only thing that differs along this gradient, or is there a salinity difference or other differences as well?
That's a fantastic question. In fact, because these are natural environments and not controlled laboratory experiments, many variables change together. However, in these springs, we try to control as much as possible in terms of their natural conditions for other variables. So we put in sensors that monitor the pH and salinity and temperature over continuous months. They were there for like 3 months, so we know the variability of the springs. The things that are different are, yes, the salinity is slightly lower, but the springs we selected to do the research at were all with salinity above 25. And other scientists that do reef research, particularly with these species, have noted that this salinity is not low enough to have negative impacts. Moreover, all of the springs had the same salinity. So the salinity is slightly lower, but not to levels that will impact negatively. The other thing that is different, which is interesting and we hope to follow up is that the nutrient concentrations that comes out with this groundwater are higher. And it might be that this is one of the reasons that the corals can calcify there, because these corals do have symbionts, and the symbionts need nutrients to grow and produce CO2, and the symbionts provide energetic resources for the corals that may give them enough energy to overcome this barrier of low saturation state and be able to calcify. However, this is still work in progress, and we have to compare springs, coral growth rate of corals and calcification rate of corals at different springs that have the same salinity, the same pH and undersaturated conditions, but different nutrient levels, to see if that is what causes or what provides them the capability to calcify.
Rick Lovett again. A follow-up on this. What causes geologically? Why are these acid springs?
Yeah, so in contrast to the volcanic springs that kind of pop out from volcanic gases and we don't know how long they are, the springs over there are part of a karst system, these caves and cenotes down in Mexico and Belize. The land formations there are limestone, and the limestone, when it rains, you have caves and caverns causing there, and then the water, the rainwater falls, goes into these caves and discharges along fault lines offshore. So these natural cave structures have been there for at least 5,000 years, probably more than that. And they're a natural feature of this karst geology that's in the coastal environment. You can see them also in the Caribbean and in other places.
Harvey Lyford, freelance. I'm just curious as to whether any comparable studies have been done or could be done on ancient reefs that are now above ground, where there's been land uplift or sea level drop or whatever.
Yes, like I said before, there are good occurrences of Pleistocene reefs from the last 2 million years or so. You see them in the Caribbean, for example. Lots of raised reef examples. I think it would be really interesting to revisit them from the perspective of the reef structure, these crests. Looking through the literature, it's actually it's really good to have these IODP, these ocean drilling cores from Tahiti, because they are, they're very well preserved. They're all in a succession, and they're very well dated as well. One of the problems of looking at ancient examples is that you often don't really exactly know the ages. You have to really interpolate ages from other information. But it would be good to go and look at ancient reefs, Pleistocene reefs, in terms of reef structure and crust formation, and see how they're responding to natural acidification effects.
I'm back at the karst. I thought that I may have this backward. My understanding is that limestone buffered acidity, and so I'm wanting to know why the water is acid. I'd kind of figured it had come from limestone caves.
The limestone does buffer acidity to a certain degree, but this is freshwater, rainwater, and it's a lot more acidic than seawater. As it goes through the limestone, it dissolves some of the limestone, and therefore the alkalinity and the calcium concentrations increase, but it doesn't, so the pH is higher than it would be if it was just fresh water, but it reaches a saturation state after which it doesn't buffer it anymore.
Any other questions for our speakers?
Liz Gallagher from Environmental Research Web. I've got a question for Robert. Could you comment about the bacterial crusts and whether they appear today, and if not, why not?
So just can you repeat the last little bit?
Do we see bacterial crusts today, and if not, why not?
Do we see the bacterial?
Yes, these bacterial crusts are calcified bacterial biofilms and mats, and of course they have actually a very, very long history going back thousands of million years. And we mostly we refer to them as stromatolites. And there are many, many different sorts of bacterial crusts. You get them in freshwater lakes and creeks, calcareous lakes and creeks. You get famous examples in Western Australia, like in Shark Bay, and you get examples in the Bahamas as well. And you get these cryptic reef crusts. And the interesting thing about these cryptic reef crusts that we've been studying is that they can be very abundant, and they are structurally very significant for the reefs. But they're not so noticeable, they're not so conspicuous. So if you go and look at the surface of a reef, you don't see them. They're forming in the dark in anoxic environments a few meters down in the reefs. And there's no reason to think that they're not still forming today locally, but they're just nowhere near as abundant as they were. So when I say they disappear, I may be exaggerating a little bit. They very likely are still forming today, but you'd have to go a couple of meters down inside a reef framework to see them. But they would be much thinner than they were 10,000 years ago when they were up to 20 centimeters thick.
Well, great. Unless there's any other questions, thanks to our speakers. Next press conference is at 10.
Thank you very much for your attention. We appreciate it.